Today we are going to cover chapter 9 from ASNT level 3 study guide. So we are using third edition, which is a latest edition of this ASNT level 3 study guide. If you've seen clearly, they clearly mentioned ET means electromagnetic testing, not eddy current testing. So ET level 3 study guide. Okay. And if you've seen the contents, total of 10 chapters. So today we are going to cover chapter 9, so which is nothing but remote field testing. So this one chapter exclusively given for RFT. So in other areas you may not get information about RFT. So if you read this chapter 9, it covers the RFT syllabus from this level 3 study guide. And also apart from this we are using a handbook and we'll discuss that one also. But if you compare the handbook information and this level 3 study guide, almost a similar information, so repeating. And even if you refer to the PTP series book, the ET level PTP series book, that one also contains the similar information, because the concept same. As long as you know the working principle and the concept, so the information more or less is a similar in every book. Okay, chapter 9 is nothing but remote field testing. Yeah, so coming to the first point, so remote field testing, so that name itself is saying remote village, remote area. So meaning your detector coil is kept remotely from the exciter coil, so the distance is more than 2 times of the tube diameter. So should not be looked as a eddy current test. It is not similar to the eddy current, because your eddy current be mostly based on the penetration of the eddy currents. If you recall the basics of eddy currents, it depends on the penetration of eddy currents from the surface. So that's what we call as a skin depth, and we used to follow those calculations, and then we can detect the cracks, all those things, mostly like surface or subsurface cracks. But here we are performing this remote field testing without using of any magnets, because if you see in other techniques like magnetic flux leakage or saturated eddy current testing, so especially if you are dealing with the carbon steel tubes, so we may need to use magnets or maybe other techniques, so that we can magnetize the tube and we can detect it. But when it comes to RFT, we are not using any magnets, but with the help of coils we are generating some magnetic field and we are using that magnetic field. So that's why it's slightly different to the eddy current testing. Okay, and to reduce the permeability effects, because your material is a carbon steel having a high permeability, so we are dealing mostly with the carbon steel tubes. Then remote field testing achieves this in the tubes or plates that are up to 5 mm thick in the case of inline inspection tools for pipelines. So if you are dealing with pipelines like cross country pipelines, so you can even go bigger diameter pipe with thickness up to 5 mm. Generally, like tubes means usually less thickness, even plates also lesser thickness. But when you go for a pipeline, sometime you can even go up to a thickness of 15 mm in steel, and you can even go up to 25 mm in cast iron by the use of low frequencies. So here the important point is this one, same like ultrasonic testing or same like eddy current testing. If you want to inspect the thicker material, so you need to use a very low frequency. Okay, low frequencies need to be used. And also if you've seen here, like mostly the tubes and plates, so we are going up to 5 mm thickness. And if you recall, ASTM is 2096, so we mentioned clearly like up to 3 mm. That is a standard practice, so general way, so they mention up to 3 mm, but here you can go up to 5 mm. But when you are dealing with the carbon steel, you can even go for 15 mm. But if you deal with the cast iron, you can even inspect up to thickness of 25 mm, because cast iron maybe permeability is different, so similar to your carbon steel, than by the use of very low frequencies. So what they're trying to say here, if you are dealing with the higher thick materials, you need to apply the low frequencies. So this is one important question. Low frequency is required for dealing with the high permeable materials or a highly carbon steel material and higher thickness materials. Then it is true that the exciter coil used in RFT probes generates eddy currents in the material, but the eddy currents are not the dominant form of energy. If you compare RFT and eddy current testing, so almost similar. Eddy current testing you are using the coils, here also you are using the coils, but in eddy current testing you are dealing with eddy currents, so you are dealing with the penetration of the eddy current into the wall thickness, but here we are dealing with the magnetic field component. and we don't bother about the eddy currents, because your eddy currents, the proximity or the area of coverage is very small, but in that location you do not have any receiver coil. For example, if you see in this eddy current testing, just imagine the eddy current design. So you have exciter coil here, somewhere you have a receiver coil. So if it is producing the eddy currents here, so any disturbance, this receiver coil will respond to it. But if you see in RFT, so what happens, you have an exciter coil here, so this exciter coil producing some eddy currents here, right? But your receiver coil is somewhere here, so longer distance. So this eddy currents do not show any influence on this, so you may not get any information of the eddy currents with this receiver coils. So simple logic, if they are very close, then it is called as a eddy current concept. If they are diverse, or maybe like the distance is more than 2 times of the diameter, then we can call it as a remote field testing, because the field is remotely received by these receiver coils. So that's why here the dominant form of energy is nothing but magnetic field, not eddy currents. So that's what they're saying here. The dominant energy source here is nothing but a magnetic field component. The magnetic field is concentrated in the material. Why? Because it is a ferromagnetic tube. So we are dealing with a carbon steel tube, and it all obeys the laws of all magnetic energy. Because same like iron attracts magnetic field, the magnetic lines always looks for a path of least reluctance, and it produces north pole, south pole, dipole movement. So all those things are like matching with the ferromagnetic material behavior. Then coming to the exciter coil, the exciter coil is used in RFT to generate the primary field. Same like your eddy current testing coils. When you give the varying current like AC current, so alternating current is producing the varying magnetic field. So that varying magnetic field linking with the material is producing the eddy currents. So that is the principle of eddy current. But here, so the varying currents producing the primary magnetic field, or we call as a varying magnetic field. That magnetic field is similar to your bar magnet. Then you can feel like a small magnet inside, and it is magnetizing the tube wall thickness. But same logic, if you go with the magnetic flux linkage tube inspection, so instead of using coil we use a magnet inside, so that magnet producing the magnetic field. But here, so this coil is producing the primary magnetic field because of the varying current, or because of the AC current. Okay, so that's why it is producing like a varying magnetic field, like time to time it is changing north and south pole, and all it depends on the exciter frequency. So if you vary the frequency, that magnetic field also varying. So exciter coils generates the magnetic fields that flow in loops. I'll show you the pictures, then you can understand. The loops of this magnetic energy gets concentrated in any ferrous materials. Why? Because magnetic field likes always this ferromagnetic materials. If you bring iron rod closer to the magnet, what happens? It will attract. Why? Because the field is concentrated more into the ferromagnetic field. So it will try to attract that, and it will, the flux lines will always love to follow this ferromagnetic material. Okay, so that's what, if you bring anything closer to this ferromagnetic field, so it is easily interacting, and the magnetic flux lines are easily concentrated into that tube wall thickness. And as the field is alternating, so you can, it also produces the eddy currents. Same like eddy current concept, the varying magnetic field again produce the varying currents, that is nothing but eddy currents. So here also we are producing eddy currents, but we are not interested in eddy currents. We are just only interested the interaction of primary magnetic field with the tube wall thickness. Okay, you can see here, so this exciter coils, so this one is a detector coil. So exciter coil is producing the magnetic field, you can see here. So looks like a north pole, south pole. Just imagine this is like something like a north pole, and this is a south pole. Just imagine this is like a bar magnet, so north and south pole. So you have this magnetic loop lines. Here also same thing. So this is also like this one is a dual exciter. So these are all flux lines interacting with this material. Why? Because this tube is nothing but a carbon steel tube. So that's why the flux lines are easily passing through this tube thickness. You can see here, this one we call as a indirect coupling. So the flux lines passing here and reaching this receiver coil, or we call as a detector coil. But inside also you may have a small field. This one is not reaching this detector coil, because the detector coil is located at a distance of greater than 2 times of the tube diameter. So what happens, this direct coupling, So here maybe the energy is very high, but when it reaches this exciter coil, detector coil, so the energy is very small, so you can ignore. But when you see this magnetic flux line, so these are all passing through this material thickness and then finally reaching this detector. So that's why we call it as a remote field. So if you keep your detector coil somewhere near to this, so this one we call as a near field. So near field technique is similar to your eddy current testing. In that, so the exciter coil and the receiver coil is almost closer to each other. But if you put your receiver coil in the middle, so you won't get any useful information. That's why we call it as a transition zone, and this is not much useful for our applications. So either we can use a near field technique, meaning keeping closer to this, or you keep at a distance more than 2 times of the tube diameter, so far field, so near and far, or near or remote. Okay, then if you seen the previous published articles or papers, so they call it as a remote field eddy current testing. So as I mentioned yesterday, so RFET also, some books they used to mention RFET, remote field eddy current testing, but as we already had eddy current testing, so it may give some confusion. So that's why they later they finalized the name as RFT, remote field testing, so that it will not give any confusion with eddy current testing. So why? Because these two groups, STM and ASME, these two groups, they are working with this electromagnetic testing. They have a committee members all, they will sit together and they finalize the name. And in this chapter, we can discuss about the inspection of ferromagnetic tubing in various heat exchanger by using the internal bobbin coil technique. So the tube inspection, same like eddy current testing. So we are using a bobbin probe inside, so which is having the coils. If you recall the design, so you have like exciter coil and receiver coil, and this is just inserted in the tube, right? So you have one is exciter coil and other one is a receiver coil. So this one is internal bobbin coil technique, and only the requirement is your the distance between this exciter and the receiver should be more than 2 times of the tube diameter. That is only the requirement, major requirement to call it as a remote field testing. And also we seen yesterday like ASME 2096, which gives this information. So the definition, if you want to see the definition of remote field testing, you can refer to this ASME 2096. So what they mention, like you have that indirect coupling. Instead of direct coupling, you are linking the magnetic field information indirectly. Why? If you see in this pipe, so your exciter here and your receiver is here. So instead of flowing this magnetic field lines this direction, so the magnetic field is flowing this way, indirectly reaching this. So indirectly reaching, so that is what we call as a beyond the direct coupling, meaning indirect coupling. So that is what we call as a remote field testing. So remote field testing is nothing but a test technique. So this is also an important question in the examination. So RFT is a technique under electromagnetic testing method, same like eddy current testing, pulsed eddy current testing, remote field testing, ACFMT, then conductivity measurement, or even paint coating thickness measurement. These are all like the techniques under electromagnetic testing method. So here also RFT is a technique under electromagnetic testing method, so which is used to detect and characterize the discontinuities. So coming to the principle, so simple principle, we have a copper wire. If you see in eddy current testing, RFT or ACFMT, it's nothing but a simple copper wire. We are just taking a copper wire and we made into a coil. Only the instrumentation to collect the data and to analyze it, so we need to use the proper equipments and specialized softwares. That's only making it a very difficult technique. But if you see the testing and understanding the principles, is a very easier concept. And here what we are doing, so the excited coil is nothing but we are just giving our AC current, varying AC current, which produces the magnetic field, and this magnetic energy travels along the tube wall for some distance in both directions. So one is along the straight direction in the ID side, and it is exiting through the wall thickness and travel outside along the axial direction, and it will reach the detector coil. So the distribution of the primary field is dependent on the magnetic properties of the tube. So if you want to have a good RFT, so your material must be like a carbon steel material, so that it will easily interact with the magnetic field. and also your tube wall thickness. If it is a very thin, so you may get a good response and good indications, but if it is a thicker wall tubing, then it will take more time to reach. Okay, and also it loses its energy as well, so that's why, so you need to ensure the field properties with respect to that material, and also the proximity of the coil, like fill factor. Here usually the fill factor is not a major requirement, so even if you have a 70 percentage of fill factor also you can accept it, but eddy current testing normally we go for 85%, 90%. Then the transmitted field may be affected by the discontinuities in the two wall. So if there is no discontinuity, so you will get a uniform magnetic field component. But if there is a discontinuity like crack or any wall loss, then what happens? The field strength will vary. So that's what, if you have any discontinuities in the tube material, so your field will get affected. Based on that, you can assess what is the loss of wall thickness, and also this is will produce you in terms of phase lag is nothing but time delay because of this particular wall loss. Then if required, you can use a special hybrid coils, like sometime you can use a dual exciter with a single detector, or sometime you can use a multiple detector with a single exciter coil. So depending on your requirement, you can use a special hybrid probes. So as I mentioned earlier, like RFT probes compared with the eddy current testing probes, RFT probes are bigger in size because of the distance between the transmitter and receiver. Okay. So, and also the high magnetic permeability of ferromagnetic material drastically impacts the standard eddy current testing. So what they're trying to say here, if you try to inspect the ferromagnetic materials where the permeability is high, if you see the equation, delta is equal to 1 by square root of pi of mu sigma. If your magnetic permeability is high, the depth of penetration is less and a bit difficult to inspect. So that's why eddy current testing we cannot apply on ferromagnetic material. So those areas we can try with this remote field testing. Some electromagnetic testing attempt to compensate, and you can use a strong magnets, like if you use a magnets or DC current driven saturation coils. This one we may call as a saturation radio or saturation eddy current testing, and also we can use MFL tube inspection techniques. But if you compare with the magnetic flux leakage, so what is the difference between RFT? So here you may not require this magnetic saturation. You don't need to magnetize to higher levels to saturate the entire thickness. But here when you are dealing with MFL, so you may need to saturate. You may need to apply a strong magnetic field. So most of the time they use a DC magnet. Okay, so make use of natural tendency of ferromagnetic material to channel the magnetic energy. So here entirely we are using the concept of allowing the magnetic flux lines to pass through the given job. Then coming to the probes, you can see here because of this distance, you can see exciter to detector coil is a very lengthy, and if you see this one is a tube diameter, so if you check the tube body, so this distance is more than 2 times of the tube body. That is what we call as a remote field testing probe, and this is a double exciter. So here you have exciter and this one is exciter, and this is a detector, and here also same thing, this one is a flexible small bore pipe, and this one it is having a large bore and with the brushes for cleaning purpose as well. Then you may have this array of probes as well. Then as I mentioned earlier, so this is called as a through wall transmission because your field is transmitting through the wall. So here, so the field is going outside, and here it is transmitting through the wall, and it is going parallel along the axis, and it will re-enter into the detector area. So this is what we call as a through transmission, because as I mentioned earlier, like same like UT. So if you place a probe, then if this guy is receiving the other side, so you can claim that this is a transparency, like easily they are transmitting. But if this one having any discontinuity inside, so you can change the signal, you can see the different signal pattern. And also if you see this figure, so if you kept this exciter coil and detector, for example these detector coils, if I kept here exactly 1D, so if I put here, so the detector coil at 1D, what happens, this technique we call as a near field testing, and this one we also call as a direct field zone, because here you are producing the field and this coil is sensing it. So that is what we call as a direct field zone. And if you kept at greater than 2 times of the tube diameter, then we call as a remote field testing. And if you keep in between, like a 1 diameter to 2 diameter, then we call as a transition zone. Okay. And also these fields I will explain shortly. Yeah. So this one red color one is a direct field, so this red color line, and this orange color is indirect field, and this one is a resultant field. So if you see the resultant field here, so in the transition zone your resultant field is not proportionate, and you may not get good results with this information. Then, as we know earlier, like magnetic flux lines always follow the path of least reluctance, meaning least resistance. Like shortcut, it will try to follow through the carbon steel material, and the flown down the tube wall, which acts as a waveguide because they flowing through the tube wall thickness, same like a pipe kind of thing. So they receive the practically all of their energy from the flux in the tube wall and the field that is external to the tube. So your detector is detecting two components. One is a near field component, other one is a remote field component. So real field means when they are close to each other. So the type interaction, or even some coils when we use, like you may receive some direct coupling information. So that is because of the eddy currents. Then the direct field from the exciter coil is almost completely attenuated, but you may receive that electric field, but that is a very small component. Okay, but when you use the externally field, like creating with the RFT probe, so it can be stronger than the electric field inside, and this is also called as a through transmission technique. Okay, through transmission technique, and through transmission normally implies that there is no source of energy transmits through the equilibrium. So these are the designs. Okay, yeah. One second, yeah. So this one is like exciter coil, and this is detector coil, and the wall thickness, the energy is flowing through this and reaching this. And if you see, this one is outside, inside you have only coil, but outside we can see like a plastic 10 case. That one is the probe, same like this. So this one is if anything reaching here, then we call as a direct technique, but if anything reaching beyond this, then we call as a indirect technique. Here you can see it. So you have a small exciter, bigger size receiver coil, exciter coil, and this one is a receiver coil. Same exciter coil, it is a passing through the passing outside the job and re-entering. So this is what we call as indirect coupling. But here, so he must apply the probe and he can take a manual readings. Okay. So as I explained earlier, so this one technique is similar to through transmission because the sound is passing through the thickness. Right here the sound is passing through the thickness, but here the magnetic field is passing through the thickness, and it is passing through the thickness two times. So that's what we call it as a through transmission mode. Okay, so the receiver element is on the opposite through the side of the mark. So the difference is simple. So you need to have like one thickness in between. For example, if you see that through transmission, so this is your plate, and you can put a transmitter here, and you can put a receiver, and this one we called as through transmission mode. Okay, so same points they are explaining here. So energy path is actually twice the wall, so it is a traveling through the tube wall thickness two times because you need to get the signal. So through transmission field is moving from the OD to the OD surface of the tube, because if you see the tube, so where you are getting the field, because of the exciter coil we are producing the magnetic field, and this magnetic field is passing through the thickness and re-entering. So the origination is somewhere here because of the coil. And for this reason, so the short discontinuities often show two distinct signals when the exciter and the detector passes through the discontinuity at different moments in time. So sometime like the tube is having a small discontinuity. So when you pass the tube, so what happens, very fast it is moving through this, and immediately she notice like here there will be like a flaw, a small one, like when you have exciter, so the receiver is in the detector zone. I mean like the discontinuity is giving some information to the receiver. When you detector also crossing, you may get another indication. So what they're trying to say here, like if you have a smaller discontinuity, so the two times the probe is crossing the discontinuity two times. One time exciter is crossing, another time is the detector is crossing. So that's what they said, like here you get two signals, and the short discontinuity has interrupted the through transmission path two times. If you see the short discontinuity, so the through transmission it was interrupted by two times. And coming to the transition zone, so if you keep the probes in the middle, like 1.5 to 2 times of the tube diameter, then you will get a transition zone. But exam point of view, they will not ask many questions are near a transition zone. So just only they will ask, like if you keep the exciter closer to the sorry, if you keep the detector closer to the exciter, what happens? So you will enter into the direct coupling zone or direct zone. So here they call as a waveguide. Waveguide or conduit is nothing but looks like this. So your energies are transmitting through the pipeline. So this is what we call as a waveguide. So in magnetic fields are modeled as a closed loops, as we know the magnetic properties. So it always produces a closed loop. And when you mix with incoming exciter energy, so you can have a transition zone, but which is less important for applications. And but if you go with a remote field zone, so it will produce a significant difference. Then the detector coils placed within the near field zone or the transition zone will not work properly. So if you put a detector coil either in near field or in the transition zone, you won't get a useful information. So you must keep your receiver coils in the detection area. So furthermore, the transition zone location is affected by the frequency applied to the exciter and also based on the material properties. So what they're trying to say here, like a transition zone is not important for this, and we may not require to focus more on that. So like you will not get anything, even if you play with the frequency also, you will not get a useful information. So that's why our requirement is mostly based on remote field, and you had another technique is a near field, but there is no like transition field technique. So you have a near field technique and a remote field technique. Okay, so therefore, so if you need to keep the detector coil, so at least you need to maintain 3 times or up to 5 times of the tube diameter. Then coming to the energy distribution, so if you see this chart, you can understand this is showing the amplitude. If you see clearly, this one is a dotted line is a ID, and this one is a OD, and this one is ID. For example, if I take these two, so this dashed line is OD, and this is ID. So if you see, this one is nothing but amplitude. So what happens here, like if your distance is more than 2 times of the tube diameter, for example 2 to 6 times of the diameter, so you can see a linear relationship between OD and ID. So if you see this 10 power minus 5, but this one is a 10 power minus 6, meaning 10 times different. OD signal is a 10 times better than ID signal, so you will get a uniform variation. But when you see here the near field, so what happens when you keep your detector less than 1.5 times the tube diameter, so you will have this ID amplitude is higher but OD amplitude is lesser. But if you go in the transition zone, so you will get like some confusing field and like some confusing amplitude, and it will not either matching with the near field or with the far field, and usefulness is less, very less. So that's why they did not focus more on this. So they will focus either on NFT or RFT. That's why they classified the zones, 3 zones. Then the driver or exciter coil, when energized with AC current, supplies a low frequency AC magnetic field which couples to the tube wall. So overall, the concept is very simple. You just need to use a driver or exciter coil. You send AC current, then automatically it will produce the required magnetic field that interacts with the wall. And this induction occurs twice in the near field or direct field zone. Eddy currents are also created, but our RFT purpose we no need to consider these. Then eddy current also created through induction. So, but as you have a receiver at longer distance, so it is not showing any impact on the results. And map the strength and distribution of the direct coils. So even if you want to get a more information, you can map the distribution of this field and you can analyze. So you can see something like this. So this one is a direct field, here is a direct field internally. So internally you have a field, and sometimes internally small portion is receiving the exciter coil, but if it is outside, then we call as indirect field or remote field. So here it is exiting from the remote, from the tubal thickness and re-entering. So overall what they're trying to say here, so you have three zones, and in three zones your amplitude variation is significantly seen. So transition zone is useless, but if you see in the RFT zone, you have a good relationship between ID and OD signals. So that's why total they classified into three distinct zones. One is a near field zone. We also call it as a direct couple zone. Sometimes they ask the name. So direct couple zone, and the diameter range is 0 to 1.5 times the tube diameter. And if you see in the transition zone, 1.5 to 2 diameters. But if you go with a remote field, greater than 2 times of the diameter. So why they mention 2 to 3 here? So like most of the RFT probes, the design is based on this 2 to 3 tube diameters. So something like this. So you have exciter coil, receiver coil, and the gap is 2 to 3 times of the tube inner diameter. And this one is a direct coupling energy, but a very small energy. And this one slightly you may add up attenuation and reaching this pickup coil. Then coming to the near field zone, so near field you may get intense magnetic interaction. Why? Because the detector coil is very close to the exciter coil. So directly you and your friends sitting together and drinking, then intense discussions will go on because face to face. Same thing occurs here, like exciter and receiver coil is a face to face and very closer to each other. Then the time you can have a good interaction. Okay, and a tube wall inside diameter surface is referred to as the near field, meaning internal field only we call as near field, because inside the tube you have exciter coil and detector coil which we kept closer to each other. So that one we call as a near field. Then within the near field zone, the eddy current generated in the tube by the AC current create a shielding effect that of the exciter flux. What they're trying to say here, so when you keep the exciter and receiver closer to each other, so it may produce this magnetic flux, but at the same time you have this effect of eddy current concept, because your field is a varying magnetic field that in turn produces a varying eddy current. So when you have this eddy current and magnetic field variations, sometimes you need to monitor closely. Then the eddy current propagates to the material, same like your eddy current basic principle concept. So it will in turn, the changing eddy currents will produce the magnetic flux, a secondary magnetic flux, which try to reduce the primary magnetic field. For example, in your company you are the level 3, for example, then your friend willing to, your colleague also willing to become level 3. So in that case what happens, so when you make him level 3, when you train him, when you guide him, he will become level 3. But once he become level 3, so he will try to dominate you and he will try to make you to resign, because he want to get next level. So that's what like the, but the reason who is behind, you are the one helping him, you are the one given the questions or explaining, so he become. So something like you need to check the secondary field. So logically, the near field zone would be an area where there is a greater sensitivity to the discontinuities because of the high concentration of magnetic flux. So you can able to detect some discontinuities in near field technique as well. So sometimes the surface of the tube, next to the exciter, you may get a strong field which masks the signals from the tube ID. So what they're trying to say here, so if you try to combine the eddy current testing, so internal areas you can get some information, but when it comes to the outside you may miss some information. So in remote field testing, to enhance the discontinuity of detectability of discontinuities on the outer wall, so you always need to place the coils at distance away, like more than 2.5 times. Then RFT energy distribution, the same graph. So as I mentioned here, ID and OD, you have a uniform relationship, but here the higher transition zone is weaker. So you can see here the video. So I'm just playing the near field technique. So you can see here the exciter and detector coils bit closer to this. So this one we call as a near field technique. So all the exciter and receiver coils are closely kept. So I'll play this video of 1, 2 or 3 minutes near field testing. Just watch. 1 minute only. Okay, so this is about a near field testing. Just as we seen in the video, so your detector coil is slightly closer to the exciter coil. Then transition zone, so the reason just outside the near field, so just completion of the near field, then you are entering into the transition zone up to 2 times of the diameter. When you cross the 2 times of the diameter, then we call it as a remote field. So it's very simple. So you have a near field, so that is a range is nothing but 0 to 1.5 times of diameter, and this one up to 2 times. So this one is called as a transition zone, and the final one is remote field zone. So 3 zones. Sometime the range also they will ask one question. Okay, so the area that is not currently contain reliable data, so you can get when you try with the change in frequency, proximity, wall thickness. So some applications you may get a better results with near field testing. In this zone, the great deal of interaction between the magnetic flux and diffusing outward from the exciter, and the flux that is returning the energy diffusing inward from the outside of. So what they're trying to say here in RFT, so we are mainly interested the flux going outside and the flux coming inside. So these two only we are very important, because here you may have a discontinuity, here also you may have a discontinuity in the tube wall. So these two only will decide. The total or resultant field strength in this area tends to be weaker because of the negative interaction of the field and differing directional here you can see here it is going this direction, but now it is entering re-entering. So because of that, sometimes there will be effect on that energy. So when we have these two opposing fields meet, the resultant cancellation of some of the respective energy. So if you like minus off, sometime you will get lesser value. Then coming to the remote field, so the third reason is an, I think this one is a transition zone, sorry, yeah. So what they're trying to say here in the transition zone, if you see the figure then you can understand. Yeah, here you can see here. So here this dotted line, that is nothing but ID, right? Sorry, this one is ID and this one is a OD. So one is positive and another one is a negative. So because of some variation, significant variation, so you may not get enough strength of the signal. So that's what they just saying, like a transition zone is useless. So two opposing fields you will get, and the final output is 0. Okay, then coming to the remote field, so the main important requirement is you need to give the gap of more than 2 times of the diameter, tube diameter, and it starts with a linear decay. Just now we seen, right? So you have this ID OD signal and ID signals, so you will maintain a linear relationship. So the signal amplitude of the ID and OD are parallel to each other and are linear after peaking at maximum values. Okay, and this rate of attenuation, so like if you see the graph, the rate of attenuation is slightly different from 10 times to the 100 times. Like one signal you can see here, so this one is a 10 power minus 4, this one is a 10 power minus 5, and this one is a 10 power minus 6. So if you compare this line and this one, so this one is a 10 power minus 5 and this one is a 10 power minus 6. So how many times different? 10 times different. And here also same thing. So it is like 10 power minus 6, and this one is dealing with 10 power minus 5. So you will have 10 times variation. Then coming to the phase is required to use here to calculate as a time delay. So used to estimate the wall loss. If your tube is a new installed tube, then you may not get a significant phase difference. But if your tube got corroded, then you can see some variation or delay in the reception of the signal, and that is what we call as a phase change. A thinner wall always gives lesser time because very thin, so very fast the flux lines flowing through it, and that's why they're saying like if you have any like significant corrosion, so very thin wall, so you will receive the signal very faster to the detector coil. And if you have discontinuities at different depths, so you can make use of the phase shift. So what they're trying to say here, for example, if 20% wall loss, you will get one particular phase. If it is a 40%, you will get a different phase angle. If it is a through wall hole, you will get another phase angle. So like the time delay, if it is a 10% different value, 20% different, 40% different, 80% different, 100% different. So that's why in the defect depth determination we need to use this phase angle versus a depth curves. So if you've seen on the instrument, so mostly they'll use the depth versus phase curves. So here the phase we also call as a phase lag or phase angle as well. In eddy current testing, there is a well-defined difference in the phase angle response between ID and OD events. So here also similar to that, you are getting the variation for based on the percentage of wall loss, you will get a significant variation in the phase angles. So you can see here, however, in remote field testing, data from ID and OD of same depth will have the same angle. But here, like eddy current testing, if the defect is on the ID side, you will get a different phase angle. If it is on the OD side, you will get a different phase angle. But when it comes to the RFT, so for example, if your discontinuity is on the OD side, so like this, or if your discontinuity is on the ID side, for example, if your same size, same depth, for example, this is a 20% wall loss, this is also 20% wall loss, if both are in the opposite direction. So here for example I got a signal like this, here also you will get the same thing. So that's what they're saying, like when they are at a different depth, the same depth, you will get almost a similar phase angle. But in eddy current testing, so irrespective of the orientation, so you will get different phase angles. So that's why RFT is having equal sensitivity for both ID and OD discontinuities. So all washless signals rotate counterclockwise with respect to the nominal tube walls. This one yesterday we explained, right? So you have a reference curve. So this wall losses, they just try to follow this reference curve, and this wall loss is following this counterclockwise direction. Okay, so this one like similar to your eddy current testing, so you can take a through wall hole. So this one is 100% wall loss, that is nothing but through hole. So you can set at the phase angle of 40 degree. So if it is coming more than this, then we can say like this one is a OD discontinuity, but if it is coming lesser, this one is ID discontinuity. So this one we call as a phase to depth discrimination. And phasor diagrams, so phase is nothing but just a time delay. So you can see here same like a sine wave. So one person start at 9 o'clock, other person start at 6 o'clock or 3 o'clock, so you can tell the phase difference, 90 degree 180 degree difference. So the same thing, so it's like a round path. Like for example, you started at India and you went to London, then London to India. So this one is a forward journey and this one is a reverse journey. So India to London and London to India, so you reach your destination. Okay, here also same thing you can see here. These are all like a three phase and this one is a single phase. So if it is a sine theta, so you will have a starting point here, but if it is a cos theta, so you will have a starting point somewhere here. Okay, and as we know, like eddy current concept, so you have this impedance also. So z equal to real time plus imaginary time. So this one is a real time resistance and this one is the imaginary part, so if you combine that, we call as impedance. Then VPPP, so voltage planar plot, which is nothing but similar to your Lysage's figures. I will show you the figures, then you can understand now. So useful representation is the voltage plane polar plot. Yesterday we shown some of these charts. So it shows the signal phase angle as well as the log of the amplitude, which can be used to accurately measure the remaining wall thickness. So what we are doing here, we are just trying to link the relationship between the phase angle and as well as the amplitude. That's why they call as amplitude phase curves. So one-sided discontinuity can be easily distinguished, whether it is on the ID side or OD side, you can easily distinguish. So this one is the chart, you can see it. So this one initial signals and this one is absolute signals. Okay, this one is a difference and this one is a differential. So 20% wall loss. So this one we call as a strip chart and this one is a phase amplitude. Then Lysage's curves. So these type of things we call as a Lysage's curves. So it's nothing but like showing the images of these RFT signals. Sometimes the interaction of magnetic field they best explain with these kind of Lysage's figures. Okay. So nothing but the interaction, same like how we see in the impedance curves. So these are all drawn with the complex planes. So these are all curves we call as Lysage's curves. Just only the phase delays varying and other. Okay. Then amplitude or voltage. So RFT senses a decrease in wall thickness as a stronger AC magnetic field cut across the pipe. So if your tube wall thickness is uniform, there is no loss in wall loss, meaning there is no damage, then you will get a constant magnetic field. But if there is a significant wall loss, then the amount of magnetic energy received by the detector will increase. So that is what they are saying, like stronger AC magnetic field will be received by the detector. So this induces the stronger voltage, meaning if the voltage is high, you can say there will be some corrosion. So discontinuity is larger volume increases the amplitude. If it is a bigger size discontinuity, you will get more voltage and more amplitude. So the smaller volume discontinuities produce a small amplitude signal. So very simple, bigger size discontinuities. So the signal strength also bigger, but if it is a weaker one, so the amplitude will be smaller. So signal phase still represents the wall loss. Okay. Then the tube support plate. So if you use a frequency mixing and other tools, so you can eliminate the signal from the tube support plates and baffle plates so that you can avoid the interaction. So metallic materials on the tube body tends to attenuate or partially block if you have any like attachments on the tube support plates. So what happens, the magnetic field is passing through that structure and it will reduce the signal strength. So because of the spacing between the exciter and pickup coils, so you will get a decreased sensitivity, because even the smaller the flux size, so you will get a lesser sensitivity. Then the next one is applications. So we can detect a small volume and a large volume discontinuities. Large volume means like bigger size discontinuities. Small volume means like cracks or pittings. So large volume sometimes the corrosion, external corrosion. So we can use this technique for testing the heat exchanger tube, boilers, piping and pipelines. So there is some limitations with this technique. For example, fin fan tubing, which found in air fin coolers. So when the tubes containing this air fin fan tubes, then you can recommend a magnetic flux leakage testing. So something like this. Sometimes maybe this one is a carbon steel, but these fins are maybe made with aluminium. So in that case, sometimes it is restricted. So large diameter fins of high conductivity material, sometimes aluminium. So those cases you need to use other technique like MFL. The induced energies in the fins themselves prevent the primary magnetic field propagation along the outside surface. Like if you create the magnetic field, then it will extend and can behave like a magnetic field. But here the concept is different slightly. Next, while RFT has approximately equal sensitivity to both internal and external discontinuities, it is a highly sensitive to the discontinuity length. So based on your length, so you will get different things. And what they're trying to say here, depth. Like if you have the depth either from the OD side or ID side is at the same depth, then you will get a equal signal amplitude. So it is having equal sensitivity for the discontinuity both either OD side or as well as ID side. But if you are dealing with a short discontinuity, it's nothing but a pits. If you have a short discontinuity pits, so you may get a second indication when the detector coil passes the what they're trying to say. If you have a very small discontinuity, so your probe is crossing this small discontinuity two times, because your exciter and receiver coil is separated by a long distance. So when it passes through the tube, so it will notice two times the indication. So that's why sometimes we can use a differential detector coil so that we can easily discriminate these kind of low volume discontinuities. So pitting and all we can easily detect with a differential coil. So the data will exhibit a doubling of the log amplitude and phase angle when both coils are under the discontinuity. So meaning when both are at the same discontinuity, you are getting these signals. So for those situations like a tube to tube fretting wear or steam erosion walls, an absolute probe coil is preferred. So here the important points is if you are looking for a short discontinuity, so try to use a differential coil, or if you are looking for any like a uniform wall loss localized corrosion, then you can use the absolute probes. So when the tube diameter increases, so single detector becomes incapable. So you need to use array of detectors. So especially bigger diameter pipe is other thing. So you need to use array type sensors. So if you are dealing with more detectors, so you will get a very good sensitivity. So especially in the circumferential array, we attach more sensors which can act like exciters and more act like receivers. So we can improve the sensitivity part. So one advantage of RFT with this inspection is like if your material is having any internal liners, like for example if your tube internally coated with a cement or epoxy or any polyethylene, so HDPE piping, any coating inside, still it is capable of detecting the discontinuities. But other technology like UT and MFL may fail, but here we can still able to manage because ACFMT can go for deeper levels. So in 2096 represents this ferrous heat exchanger tubing. Okay, so here they'll tell the minimum detection capability and apply the proper tools and techniques to perform the inspection of heat exchanger tubes. Then coming to the application, so this one is a smart pick. We also call as ILI tools, inline inspection tools. So mostly MFL and ultrasonics. So they use these kind of inspection inline inspection tools, ILI tools. But even nowadays, the bigger pipelines like cross country pipelines, so still you can use RFT also. RFT also had these kind of picking devices. So heat exchanger tubes, small tubes, the boiler, so you can inspect small diameter rigid probes, and the thickness diameters is almost is 15.87 half inch to 1.5 inch. Then you have a good sensitivity to corrosion, erosion and pitting. These three type of discontinuities we can able to detect. Then next one is a boiler tubing. So this one is a boiler. Inside the boiler you may have like a 2-inch or 3-inch tube diameters, boiler tube diameters, carbon steel. So even you have like a large diameter flexible probes, you need to use a bigger size probes because you need to maintain the minimum fill factor of 0.7. Then most tubes are in between. You can see here like a 3-inch diameter, so it's a 1.5 inch to 3 inch, and you can use a small fill factor. You can see here, so the probe diameter is smaller compared with the tube diameter, so we can say like a smaller or medium fill factors. So bends, so sometimes because of the permeability variation you may get some signals, or sometimes you need to go for the trails. Then underground pipelines, especially the buried pipelines, so we can use these kind of snake tools, so they call it, I think, snake type of tools. So with that we can even collect the data and you can cover the longer distances. And here also same thing, like a 2 inch to 6 inch, I think 300 mm, so it's I think 12-inch pipelines. Then surface RFT probe, so something like this, if you have any like fixed boiler tubes, so you can use surface RFT probes as well. So these are all like we can use for tank floor inspection or any plate like materials or any boiler water wall or paste nets. So these we can by attaching, so by using these kind of scanners we can attach and we can scan the entire pipe wall thickness from outside. So instead of using ID side we can attach on the OD side. Then the last one is characteristics and limitations. So you can see it is a very good technique with the ferromagnetic materials, and you can get an accuracy of within 10% to need convert 18 degree of the diameter to be detected. So you can detect this internal pitting, external pitting, cracks, corrosion, and tube support plate variations. So but if you see in here, the pitting is good, acceptable, but our main intention is not to detect the pitting. So main intention is to ensure the remaining wall loss, so that's why RFT is limited. Okay, so this one is a good technique, and this one also good technique. Corrosion is a good technique, very good technique. Okay, so this is about chapter 9 RFT. So it took almost 1 hour.